So let's talk and let's continue on K-means. So there are two questions that is left we talk about in the last lecture. One is how to choose K. Right, in practice, say we don't give you the number of cluster K. How do you choose it? The second thing is how to choose initial mu smartly. And obviously this is very important. And we have mentioned all these K-means and algorithm is very sensitive to those initial conditions of mu's. So let's ask the first question, how to choose K. One of the way that you might think about is I can work with all possible K from say like 2 to the 10, like say you choose K to the 2, 3 to the 10, then you calculate this like distortion value, which in this case is J with respect to K, and you calculate all of that. Then you find the K that to minimize this J of K, like what we did in supervised learning, because in supervised learning, K is such kind of like hyperparameters. Because in supervised learning we have, for the test data set, we might have something like U shape, right? You remember on the hyperparameter cases, if we plug in the new data, you will have some like U shape. That there will be optimal parameters K, if K is some hyperparameters. But this won't work in clustering, because if you're trying to calculate this distortion value with respect to K, you will find out this J of K versus K is always monotonically decreasing. Okay, so there's no such kind of like minimum that you can choose in general. So in general, so if that's the case, is what we do is we're going to choose something called the elbow of the curve. So at this curve, which the minimum of and after this point, the minimum of distortion value start to decrease slowly. So you think about this as a curve. I'm choosing the elbow of this curve. Before this point, this distortion values decrease dramatically or rapidly. But after this point, then this and the distortion value start to decrease slowly. So you actually think about as a second order derivatives, and instead of first order derivatives. So first order derivative, you think about assign the first order derivative equal to 0. You are trying to find out the local minimum. Here you can think about we're trying to find the second order derivative equal to 0. That will be the elbow point. Okay, so and everything else is just being like expected. So elbow method is we hope to determine the optimal value of this hyperparameter K. So what we do is we run the Lloyd algorithm over a loop for an increasing number of class K. Say you set a range of the K from 2 to the 10, for example. Then what you do is you plot the minimum distortion values versus number of the cluster K. So here I said the minimum of distortion value is because you need to run K-means for specific K at least 10 times. So you have 10 different distortion values. So you pick the minimum of that instead of and just run once. So that's why this is important. You actually have to pick the minimum of distortion value versus the cluster of K. And also, if you plot this out, you will find out minimum distortion value actually decrease as the K increases. So there's no such kind of U curve that you can and to help. Then at last, you are going to select the value of K I'm at elbow. Elbow means after this point, the minimum distortion value start to decrease slowly. Okay, so this is the code. So we are going to using the same data point. So we have 1, 2, 3, 4, 5. So this actually has a 5 different clusters. And you find out this code is kind of different. So the reason I do it this way, I would suggest you to see and be carefully. So I'm using a different but much more efficient way to implement. But if we, the code that we do is we're trying to vectorize this as much as possible. And with that, it will be hard to interpret. And sometimes it's like, and you need some practice and a trial and error to test. But in general, you should be using this code. Use this code in your homework. So I want to emphasize, I expect you to modify this code. If you don't do that, just like randomly using ChatGPT to generate a code, I will consider this is not correct. So you actually have to modify this portion of code in your homework and to make it work. All right, so what you do, and this is the step 0, which is the same. We randomly pick, and we still randomly pick K different initial like mu as my, we just ran, and the randomly pick K points as my initial guess of the centroid. So we have our distortion list. Now the key differences here is this distance. Here distance here, I think I'm missing here. I think this is sum of x is equal to 2. So previously, I using a for loop to calculate distances, which is way too expensive. So what we do is we just using this vectorized version. So basically, each of x subtracted into this centroid 1 by 1. Then we make this centroid from like 1 dimension. Into like 2 dimension into 3 dimension. So this whole things will be much more complicated if you look at this. Right, so this x right here is a matrix, which is m by d. So this centroid and introducing this new axis, this becomes, I believe, is d by k by d. Yeah, wait. K centroids, yes, k by d by 1. Okay, so that actually becomes a like 3-dimensional array. Then this subtract that, and I'm going to take square and take the square root. Then average out on the on x is equal to 2. This is equivalent with the K-means that using a for loop to go through and to go through this loop 1 by 1 in K-means 1. So this part, so we avoid this loop and using this vectorization tricks and significant speed up the calculations. So by the end, you are actually getting a distance. So this is actually m by k. So basically, and what you got, I mean, this distance is for each n by k, and for each entries, that will be the distance. And for the first one, that will be, say, this is of xi, this corresponding to the cluster of 1. So this is the, I mean, distance between xi to the cluster 1. This will be the distance between xi to the class 2 and so on. So these are all like and the distance between and each samples to and to each class and to each centroid. Then what you do is you adding this and you and you find the minimum of the distance for each row. Then you sum so then you sum them together. That will be your like and the distortion values. Right. So this is very simple. So and because we are going to assign all the membership of each point to its nearest centroid, that corresponding to the index of this each row, which and which minimize that index and which minimize the values. So and that's also give you those indexes right here. So that will be argument of distances, but you work on the axis equal to 0. So everything right here, we did that without using any for loop. So all these three things, we vectorize it. So we use no for loop. So this will significantly speed up the process. Okay. And also right here, calculate centroid right here is we grab. So this is, I mean, still the and comprehension things. We're still using one for loop here. So this is range of k. But this is a very small for loop. I mean, can be done very quickly. I mean, at the end, so you just pick for each k from 1 to the k and calculate the centroid and for the clusters. And also, the step 3 is exactly the same. I mean, if the centroid, I mean, doesn't change, I will stop. If it changes, I will keep running. So at the end, you will output the centroid, the closest, which is my label, and my distortion list. Right. So the most important part is right here. Previously, this is really expensive, but now we get around that by like vectorizing everything. Okay, so and also this we using the time and which is and to time out how long does it take to run everything. We are going to run with a bunch of k's. So here is basically a k from 2 to 12, which is a lot. And for each of that, I'm going to run. Wait. I'm going to run. I'm going to run one. Wait. Yeah, I'm going to run 20 times here. I think it's 20 times. Yeah, this is. I mean, this max iteration is 100 times right here. So this is I'm a little bit confusing here. So here we are running for each k we run KMeans. KMeans 20 times with random initializations. So basically, we run this k-means 20 different times, and for each time you're going to have like random initialization of mu, and then this is being done right here. So in total that you actually are going to run. So this we have so 11 11 of that, and each of this you have a 20. So this is what so you actually need to run k-means 11 times 20, which is 220 times of the k-means. And since I don't need to know this like whole distortion list, because this is always monotonically decreasing during the k-means. So what actually matters is the last one, so which is the minus one here, and that will be stored into distortion current Ks. After running 20 times, I'm going to just get the minimum, which is, and with like 20 and 20 like random 20 random in the simulations. So what actually cares is the minimum of this, distortion values. So this will be stored in the distortion Ks, the corresponding indexes here. Okay, so what you actually, going to plot is the distortion Ks versus the K. Okay, so this is a very important part. So if you actually run this, you will see it only take about 18 seconds. So you can try it with my old code. This will be significantly more expensive. So, and the reason is right here. Our implementation is really, really efficient right here. All right, so if we actually plot the Ks versus distortion Ks, and like distortion and Ks, as I said, is the minimum of this 20 independent run, you will see this curve right here. This curve right here, you can see this is actually always decreasing from 2 to 12. And you can see this is very important. If you're trying to find out the optimal K right here, and there are a bunch of choices, it could be 4, it could be 5. So you can say the optimal K could be 4 or 5, it doesn't matter. Just pop and possibly 4, possibly 5. And this will be your elbow of your curve here. And obviously we know 5 is the the truth. So and of course 5 like fits into this elbow method's results. All right, so this is and how we actually and find out the optimal case in k-means clusterings. So this is how we determine the optimal K. All right, what else? So this, and the next we are going to to talk about the initialization of the centroid. There are multiple ways to do it, and of course, and we do it this way, that we repeat k-means 10 times or 20 times with the different and initializations, and these initializations just being random, and pick the one has the smallest distortion values. So this whole thing and this method actually the behavior will be worse and worse when dimension is large. The reason is when the dimension is really large, it's really, really difficult to find out a good initial like conditions, because of number of choices will be a lot. So that's why and it is a very famous algorithm called K-means plus. So this is actually a smart centroid initialization techniques. So I want to emphasize right here. So this is just an initialization techniques. It has nothing to do with the K-means algorithm itself. So just a way that you're trying to pick a better initialization point. So so this whole idea is very, very intuitive. So let's go back to this picture right here. So the idea is the following. If you think about and what is considered to be a bad initialization, right, in general. So the bad initialization says if my initial point is really, really close to each other. So that means if I want to pick 5 points as my initialization, if I pick right here, right here, right here, right here, right here as my initialization, this is a bad initialization. Why? Because these initializations are too close to each other. And if the initialization point is too close to each other, it's very likely you are, and hit to some local minimums, because there are a lot of points right here, and here are completely unexplored. Okay, so a general consensus is, so in order to have a good initialization, these points should be spread as much further away as possible. So a good one and a good initial point, that will be if we pick right here, right here, right here, right here, and right here. So these will be good initializations. Since we're using this like data point as our initializations, a good initialization, that means I want to spread mu j's as further as possible. Okay, so this is considered to be a good initialization. But again, this good initialization just being said, this is likely that will pick up these 5 clusters, but still there's no guarantee. But with this is has a and possibly has a higher chances. So this is precisely what I'm trying to say here, that this is actually a probabilistic so initialization. So basically I want to spreading out this K initial centroid as much as possible, as further as possible. So a common questions during interviews is, what is K-means plus is doing? The K-means plus doing is just an improved initialization. It has nothing to do with the K-means algorithm itself. It serves a purpose that can come up with a better initialization, such that this initial mu j's, it will be sampled as further as possible. So what we do is we choose a first central uniform at random. We still pick 1 point, the first point, to be random. Then what you do is, for every point, compute distance from the nearest previously chosen central. So basically, say you have a bunch of points right here. Say you just randomly pick a point right here. Then you calculate the distance for all other points to this point. And out of all these distances, you're going to pick the one that is furthest from the current random point, which of course will be this one. Because this point right here is really the furthest to this current random point. Okay, so this is what I'm saying. For each data point, compute the distance from the nearest previously chosen centroid. Next, and this is basically and what I'm saying, like select the next centroid from the data point. That probability of choosing the point of centroids is directly proportional to the distance from the nearest. That means the point have high and the maximum distance is more likely to be selected as the next centroid. But this is basically, we are going to using a sampling algorithm to sample the next centroid based on the probability is directly proportional to the and the distances. And for simplicity, and we can actually and write it out the and the probabilities as follows. So this is basically the probability. The next class centers to pick X or Y, it has the following probabilities, which is D squared and divided by the normalization factor. So this D right here is the minimum of the current point to the previously chosen centroids. Okay, so this is also, you have to loop through all possible current chosen centroid from 1 to t minus 1. Of course, we can make it really simple that we always and a simple modification here is always choose the maximum distance. Okay, so that means I always choose the point that give you the maximum distances. So if we do this way, and of course we just repeat step 2 and step 3 until my K centroid is being sampled. So that means I actually need to sample K minus 1 of that. After we sample this K centroid, then we are going to apply the standard Lorry algorithms with these like new initialization skills. If we choose such kind of method, it's more likely these points are further away from centroid are more likely to be picked, such that it's more likely to reducing the distortion values. Right? So as I said, if we just happen to pick these, it's more likely to be much more spread out. It's more likely to and to identify these 5 clusters. And of course, there's no guarantee with that. Just being said, it's more likely. In fact, we can prove this simple trick can provide an improvement in these distortion values. Although we still don't have guarantee of global minimum, but this and construction error is never more than log of an order of log k away worse than the optimal. So this is really, really close to global minimum. Right, so this is really, really and appealing right here. All right, so let me just let's just implement it and let's see how this actually works. So you can see we are taking this initialization for K-means plus algorithm. Step one, initialize the centroid list and add the randomly select data to the list. So basically, in this case, we just sample one of that. And then that will be my centroid for the first point. So that means right here, I pick a like data, and these are my data point. This is my current centroid right here. So this is being purely random here. So next, I'm going to using this current pick the centroid to compute the remaining centroid. So what we do is we initialize a list to store the distance of the data points from the nearest centroid. Compute the distance of point from each of previously selected centroid and just store the minimum distances. So that means you are going to loop through all possible points right here and calculate the distance between examples to the previously calculated centroids. This will be distance. You're only going to store the minimum of the distance into the DIST matrices. So this is what I'm doing right here. Then you are going to select a data with the maximum distance as our next centroid. So this is a fundamentally slightly different from my step 3 right here. In my step 3, in K-means plus, initially it should do a sampling problems with this following distributions. But of course, the point have the maximum distance from the nearest centroid is more likely to be selected. So that's why I just make things to be probability 1 as the simple, so kind of simplifications of the step 3. So this is actually a simplification. So I don't want to work on sampling. Sampling is quite expensive. Let's just select the data points with the maximum distance as our next centroid. So this will be, what I'm going to do is I'm going to take the an argue max of my distance. So these are all my distances. I'm going to find the index corresponding to the maximum distances to the current chosen centroid. That will be my next centroid. Then I'm going to stack my next centroid to the current centroid. So this will be my any new centroid right here. So for example, right here, we have, say this is the first point that I pick. And out of this first point, we're going to pick this point because we know this point right here, the distance is the furthest away from the current point right here. And this will be my second centroid point. So from these 2 points and previously, select centroid, then we're going to pick the third point right here. So this third point is actually, it's the furthest away from these 2 points right here combined. Then we continue iterate. This is my 4th point right here. And this is my 5th point right here. So if we pick these 5 points, so we can almost ensure these 5 points is as much further away as possible such that it's more likely to capture those and the global structure of the data. And of course, it's more susceptible to those outliers. So that's why always pick the maximum is not really the ideal situations. However, we are just trying to illustrate that with this simple idea. So if we're choosing this 5 point as my initial guess of the centroid, then we run this K-means plus, but this time we don't have a step 0 because step 0 is already being like resolved from the K-means plus. So I'm going to create a centroid, and I'm going to passing this centroid into my K-means algorithms. So you can see right here, my K-means algorithm is not exactly the same as before because I don't have the step 0 anymore. If you actually do it, you will see something like this. Right, so this is the initial guess. We have 1, 2, 3, 4, 5 different cluster. But if you keep running this, it will end with, it will stop with 11 iterations. We're getting 1, 2, 3, 4, 5 different clusters. But you can see this is, I mean, this is like not, and obviously, I mean, it's not perfectly capture these 5 cluster, but it's like still like significant better than before. So you can see, and there's, I mean, so I want to say this is not always giving you the and the lowest value, but this will give you like reasonably good values. I mean, in order to get like global minimum, you have to keep trying again. But the result that you got will be log k away, an order of log k away from the global minimum. But you can see this is and a significant better because right here you can always think about these two as being one cluster. So that's why technically you only have a full cluster if you think this way. And of course, this initialization will be computationally more expensive than standard K-means, and the runtime for converge optimal, like and also dramatically reduced for K-means plus. Because the centroid initially chosen are likely lie into a different cluster already. So as we said, if we choose our initialization all into one cluster, it will take much longer time to converge. However, if we choose this 5 point, it's more likely these 5 point are already lies in different cluster. So the converge time will be significantly and smaller, and my runtime will be faster in general. So this is just a very much heuristic argument from the K-means plus and from the K-means plus algorithms. But of course, that just being said, you actually have to try that out and to test the the result for the K-means plus and the K-means and algorithms. All right, so there are many other applications for the K-means, and you can work with image compression as well. So what we can do is we can cluster the point with the similar pixels. And for example, right here, you can see this is, we have the image. So this is actually the image of raccoon. And you can see each value right here and represent a pixel values for that specific point. And what you can do right here, we have all different values from 0 to 225. So that means you can and think about the whole thing as has 256 possible values. But what we can do is we can only using maybe 2 or 4 colors. That means each images we're only using maybe four different values of the pixel values to approximate these images. So what you can do here is and you can apply this and the K-means and algorithm here. I'm using scikit-learn packages, but in general, I mean, this is just trying to speed up things. So you can see if k equal to 4, that means I'm only using 4 different pixel values to actually to represent these images. And you can see right here, it did actually pretty good job, and it can get very and good textures of these images. And for example, you can see this and for like k equal to 4, and for this face and compressed, it only has 4 different unique values, which is 31.6, 85.96, 133.1, and 184.73. Okay. Previously, the image value that we have is from 0 to 255. So instead of we using 256 values to represent these images, pixel values, we're only using this 4 different values to represent this image. You can see this is doing fairly good job to represent this image. If we're only using 4 different values, this can significantly compress these images. So that's why and storage that needed to represent these images will be significantly smaller. There are other issues I want to talk about on the K-means. There are a lot of and the limitation on the K-means. For examples, if we're trying to work on this kind of moon shape data set, which is non-rounded cluster, this turns out can behave really bad, and it will classify these and this branches and this branch to be one cluster, and this branch and another branch to be another cluster. If you are working with a non-rounded cluster, K-means usually give you wrong result. If you want to cluster with the different densities, like this type of data set that we have already showed that in our demonstrations. If we're using K-means, it's more likely we'll be separate this big clusters into 2, and rather merge these like dense clusters into and like 2 dense clusters into 1 cluster. So this is, and like this situation you have seen right here. It actually merged these 2 clusters into 1 and separate these 2 clusters and separate this cluster into 2. So this is more likely to happen in K-means class. In terms of K-means clustering. So in K-means clustering, it basically assumes the data has roughly the same densities. If you are working with the different densities, K-means may not work very well, as I just demonstrated. And also, to summarize everything, K-means is a clustering algorithm aiming to minimize the total variances within the clusters. So basically, it's a sum of the square Euclidean distance to the nearest centroid. It has the following running time. So the running time is n times k times I. I is the number of iterations. For each iterations, and time that actually needed n times a k. You can reduce like various constant factor using the tricks, but still overall that will be n times of k because you need to loop through every point and calculate each point and calculate the distance between each point to and to the centroid in the clusters. So that will be k different centroids. So that one, and in that senses, for each point you have to calculate distances to k different centroid, and you have to work through for all n different points. So that's why for each iteration you have to calculate n times k order of the distances. So that's the n times k comes from. So this k-means is actually solved by something called an algorithm using this kind of alternating minimizations. Although we can guarantee that my objective, which is my distortion values, is monotonically decreasing, but it still suffered the suboptimal solutions due to the non-convexities of the optimization problems. And we also mentioned about how to choose the k, and the way to choose k is to use the elbow method, and which is you run the k from 2 to the maybe 25 or 20s, and you run the k-means for each value of the k. Then you plot the distortion values, minimum of the distortion values with respect to k. Then you will receive a monotonically decreasing functions as k increases. You are going to choose the k that is being the elbow of the curve. So that means this is decreases faster, and after this elbow point, the function decreases slowly. So in this cases, there will be 4 or 5, but it's up to you to choose the optimal case in these situations. At the end, we talk about how to improve the initialization methods by introducing the k-means plus algorithms. The whole idea of the k-means algorithm and the k-means plus algorithms is we want to choose spread out centroid at random from the data samples. If we choose those centroids as much spread out as possible, it's more likely those centroids will be lies in different clusters. So this will significantly speed up the convergences and will be less time for the iterations. And also it's more likely this distortion values, the final distortion values will be smaller. So because this is more likely to be a smart initialization schemes. So we implement all methods from scratch for the k-means, for the k-means plus. And for the k-means, I implemented with the 2 methods. The first method is I just implemented without considering any performances, simply using bunch of for loops to implement that. But this will not be efficient if you actually want to run a large data point and also various different times and various different case. If you're using my previous algorithm to run for 10 times with like all possible case, it would take a really, really long time. So what we do is we significantly improve the methods by introducing this like 3 tricks that we talk about using the vectorizations instead of using for loops. So this is a trick that I hope you can understand, you can master as the course progresses. So this is very, very important, particularly when you are handling with large data sets. So these techniques, you actually possibly need to know that in the later of homeworks as well. Otherwise, you will need to wait 2 hours, 3 hours for this program to finish. Okay. So I hope this is clear enough, and I would suggest you to go back and to study all these code by yourself and run this code line by line to understand what we are trying to do and how this is being mapped to the pseudocode and algorithms. So I hope from these examples or this algorithm, and you can tell there is a significant differences between math, pseudocode, and from pseudocode to implementations from scratch. And from implementation from scratch, then you need to consider the performances of the algorithm, particularly when data set is really large. So, and for each step, you need to think, you need to and test and to find out what is the best methods, and to improve your algorithm in terms of accuracy and also performances, which is the speed. All right, so that's all for today.